Hello everybody, my name is Johan Nilsen. I am a fire protection engineer and I work at a consultancy firm called Brandskyddslaget in Sweden. Today I'm going to talk about numerical simulations I've done on compartment fire experiments with an underventilated fire and with the ventilation supply positioned adjacent to the floor. This is the agenda for my talk. I'm going to start with some background and thereafter continue with a brief description of the fire experiments. Thereafter, I'm going to talk about my FDS simulations, my setup results, and lastly, some conclusions. A common way internationally to protect from smoke and fire spread through the ventilation system is by stopping the fans and closing fire dampers to each fire compartment. And this is an effective method, but it's also a quite expensive method. In Sweden, we have the possibility to use performance-based design when designing the protection of smoke spread through the ventilation system. A common design is to keep the fans in operation in combination with non-return dampers on the supply side. This leads to a limited amount of fire dampers, and the approach is commonly used in, for example, residential buildings and hotels. However, during the last decade, an alternate approach has been examined, and that is a method based on the same basic principle as the one previously mentioned. The fans are kept in operation during fire. But instead of using non-return dampers on the supply side, the supply diffusers are positioned close to the floor. The main theory behind low-placed inlet diffusers is that the greatest risk for smoke being spread through the ventilation system occurs in the initial high-pressure stage of the fire. During this stage, we have a pressure buildup and the smoke layer reaches the floor. At the same time, the fire are limited due to the available oxygen in the room, and we also have a smoke stratification in the room, meaning that the volumes that are being pressed out through the supply duct are both quite clean and both quite small in amount. And as soon as we have a pressure relief, for example, if a window breaks, the spread through the ventilation supply side will stop. This concept has been tested in several times in Sweden in different experiments, all indicating that the concept works and that low-placed inlet diffusers could be used to prevent or significantly reduce the spread of smoke through the ventilation system. The last done test was a series of full-scale tests conducted at RISE in Sweden in 2021. And those tests are the basis for my work. Here we see the fire compartment from the full-scale tests. The room measured 4 times 5 times 2.4 meters. The walls and roofs were built with wooden stud covered with fire-rated gypsum boards on the inside. At position A, we see the supply duct, positioned with upper edge 200 millimeters above floor. At position C, we see an exhaust duct, and at position B, we see a leakage duct, which was closed during the experiments. During the tests, they did different measurements of temperature, pressure, volume flow, O2, CO, CO2, both in the room and in the ducts. And before each test, they did leakage tests. Here we see the exhaust duct to the left and the supply duct to the right. As you can see, quite a simple system. In the experiments, 3 different kinds of fires were used, called prism fires, natural fires, and T-squared fires. They also did tests with different ventilation conditions, varied from open ducts to cases with mechanical ventilations. In total, 18 tests was conducted. Only in the T-squared fire tests, the heat release rate was given as an input, and therefore my work is limited to these tests. During these fires, they used a gas burner with fuel comprised of 95% propane. Now on to my simulations. I have used version 6.7.9 for my work. I have used a 5 cm grid, 1 mesh, and I have built the geometry and used material data as close as possible to the experiments. I have simplified the fuel to be 100% propane. The heat release rate was known from the experiment, and I used the HVAC model to simulate the ventilation system. Here is a brief description of my ventilation system. It's a quite simple system containing of different nodes, ducts and fans. The fan curves was set according to the manufacturer. We used a program called Program Flow System, PFS, to calculate pressure drops between nodes, and I thereafter recalculated them to losses used in FDS. I ran simulations without a fire in order to see that the flows matched the experiments. I have done simulations with different extinction models. I started off using the default extinction model for version 6.7.9, which is extinction model 2. I changed the auto ignition temperature and the critical flame temperature in combination with an exclusion zone locally over the burner. However, for different reasons, I did not choose that path in the end. AIT is very grid dependent, and I wanted results that were as generalizable as possible. Also, from version 6.7.9 to 6.8.0, the default model is changed to extinction model 1, because model 2 has proved leading to too much suppression in underventilated fires, and also that works less well with the coarser grids. Therefore, I changed to extinction model 1. I have done simulations with extinction model 1, both with default settings and changed settings regarding free burn temperature and lower oxygen index. Now on to some results from a fast-growing fire with active ventilation. Here we see results of the mean temperature in the room. The blue dotted line are from the experiments. The black line in the bottom is from a simulation using the default setting from extinction model 2, which leads to too much suppression and an underestimation of the mean temperature. The black line in the top is from a simulation using the default setting for extinction model 1, which leads to an overestimation of the mean temperature. The black line in the middle is the used setting, which is extinction model 1 in combination with adjusted settings regarding free burn temperature and lower oxygen index. Now on to pressure. Before each test in the experiments, they did leakage tests. I have recalculated the leakage rates to a leakage area applied in FDS. I use pressure zones to simulate a bulk leakage through walls and ceilings. And I have also adjusted the leak pressure exponent and leak reference pressure to better match the experiments. As you can see, FDS, to quite a good agreement, is able to catch the pressure from the experiments. The most important thing when it comes to low place supply events is the volumes being spread through the supply duct. Here we see the results of the volume flow. And as you can see, FDS matches the experimental data in quite a good way. And here we see results of carbon monoxide spread through the supply duct. Again, the blue dotted line represents the experimental data. And this is the tricky part, since the production of CO and soot massively increases when the fire becomes underventilated. I have done several simulations, both using one-step simple chemistry and two-step simple chemistry, as well as using different yields as an input. If we first look at one-step simple chemistry and yields based on well-ventilated conditions, it's hard to see here, and the lines are more or less flat. But with this setting, we do not capture the spread of CO at all. If we instead look at this line, we see results from using the same yields, but instead using two-step simple chemistry. This time the magnitude of the peak better match the experiment. However, the total amount spread are slightly underestimated. In other simulations I've done, and this was also observed, the peak corresponds quite well, but the total amount spread are slightly underestimated. The last line here represents a simulation using the one-step option, but instead using yields for underventilated conditions. And this setting leads to a big overestimation of the amount of CO spread. So this is a tricky part, for sure. And as you can see, there's a small time difference between the peaks in FDS and in the experiments. And this difference occurs in all studied scenarios. Probable explanation is that the gas temperature in the experiments passed through drying equipment before analysis, which meant that there was a certain time lag before analysis was done. If we compare the time of the peak of CO in the experiment, seen here, with the pressure in the room, we see that the peak occurs at the same time that there is a negative pressure in the room, which is not reasonable. If the time lag to analysis had not been present in the experiment, it is likely that peaks from the experiment had coincided in respect of time with the results from FDS. I have done a grid resolution study and concluded that 5 centimeter grid cells in this case are sufficient. It's a bit hard to see here, but the results with 5 centimeter grid and 2.5 centimeter grid more or less converges and are closer to the experiment than the coarser grid. Some conclusions from my work is that FDS is able to simulate scenarios as they described with low placed supply events, even though the fire becomes unventilated. Several outputs to a high degree matches the experimental data. However, careful considerations need to be made regarding, amongst others, the extinction model, and there is a challenge doing the results generalizable. Especially the prediction of species is a challenge. Two-step simple chemistry works to some extent, but leads, compared to experiment, to a slight underestimation of the total amount spread of CO. That was all for me. Thank you, and I welcome your questions.
Hello. Hey, Johan. How are you?
Hi. I'm fine.
Good to see you.
Thank you. Yeah, you too.
Thank you for joining us today. I know we have at least one question in the room, and then we'll see where that goes from there.
Yeah.
Kevin?
That's very good work. I've done similar calculations using the PRISME data. Are you familiar with the experiments from the French nuclear authorities called PRISME?
Yes, I am.
Okay.
I looked into those results, and yeah, they were done quite a few years ago with an earlier version. But,
Yes.
Yes.
Yeah, because they also measured these various things like CO. But my question is, what was the lowest oxygen concentration in the, well, either in the experiments or in the simulations?
Well, I don't have the exact number in my head right now, but I think it was a bit lower in my simulations than in the experiments, and I think it was about 5, 6, 7%.
Okay.
As close.
Okay.
I think.
Yeah, because in my simulations with underventilated compartments, I often find that it's not until the oxygen level gets down to close to zero that you start to see, that really large increase in CO production. So I was just curious, what your oxygen levels looked like in the compartment.
Yeah, I think it was about 5%.
Okay, thank you.
And for the CO production, did you integrate the area like under the curves of both experiment, and was it essentially the same sort of mass production, but one looked like a very narrow and tall spike and the other one was wider and shorter, but is it basically the same, I guess, mass produced?
Well, when I used the two-step option, the peak was the closest peak to compared to experiment, but the total mass spread was slightly underestimated.
Okay.
Using the two-step option.
Okay. Any other questions? Is there any follow-up work for this to continue in the future?
We'll see. We have a current research project that is ending now in October, so we're gonna sum up the work and write a report, and then we'll see.
Okay. With that, I was going to ask. Yeah, go ahead, Kevin. I'll ask.
You can ask the question. Right, you said at the beginning that they're thinking of a way of handling ventilation.
Okay, yeah, does this, did the modeling and the experimental work, does that help support or go against your change in strategy that you mentioned at the beginning for ventilation?
Well, I think it will help us. It shows that FTS is able to simulate these scenarios, but we also see that it is a challenge using FTS when it comes to underventilated fires. So we're looking at a simplified approach where we are not simulating the ventilation system using the HVAC model, We only simulate the compartment, and the compartment is only connected to the ambient through leakage. And in the simplified approach, we only take the temperature output from STS and use the temperature as an input to PFS, not a program. And with PFS, we calculate the volume being spread.
Okay.
So that is another method that we're looking at.
Okay. And do you think the ventilation strategy using the lower supply side and the upper relief vent, do you think that that's an effective way to manage ventilation in these fire compartments into exhaust?
Well, I think it's a possible way to handle it. I don't think it's going to be the most common way, but it's another tool in the toolbox, and I think it's a possible way to handle it. Yeah.
Okay. Thank you. Okay.
Thank you.
I'm not seeing any other questions, so thank you very much for the talk and for being here for us for Q&A. Have a good
Thank you.
evening.
You too.